Hi, my name is Alec Saitman. I am currently an associate professor of pathology and laboratory medicine at Oregon Health and Science University. And today we'll be talking about clinical mass spectrometry and hopefully be able to provide a step-by-step process on how liquid chromatography and mass spectrometry come together to make a unique and important contribution to small molecule quantitation. So we have two learning objectives. The first is to really explain the principles of liquid chromatography and how chromatographic separation improves specificity, sensitivity, and interference reduction. And then we'll also compare operational principles of tandem mass spectrometry, or sometimes called quadrupole mass spectrometry, and time of flight mass spectrometry, which is sometimes called TOF. And how they differ in analyte quantitation and identification. So I want to first start with some confusing language. There's a lot of acronyms that sometimes mean the same thing. The first one is high performance or high pressure liquid chromatography, which is sometimes called HPLC. That's in contrast with a simpler naming convention, liquid chromatography, or LC. Sometimes you see variants like UPLC, which stands for ultra high pressure liquid chromatography. The point of this is that both of these are synonymous in the context of mass spectrometry. Sometimes liquid chromatography is combined together with mass spectrometry, so sometimes you see LCMS. Sometimes you see liquid chromatography tandem mass spectrometry, or LCMS. We'll define what those differences are later on. Sometimes you just see mass spectrometry like mass spec or MS. Sometimes you see tandem mass spectrometry, MS. Sometimes you see time of flight mass spectrometry or TOF. For example, in my lab, we have LCMS MSs, so we have triple quad mass spectrometers that are connected with liquid chromatographers, but we just call them mass specs, just in general. The point I'm trying to make is that LCMS is two different instruments. You have liquid chromatography or a liquid chromatograph, the LC, and you have a mass spectrometer. And these are not always connected together. For example, you can have HPLC or LC instruments that help physically separate compounds and then have a different detector at the end, like UV visible light. For example, we use HPLC to quantitate amino acids, but it's not connected to a mass spectrometer. On the flip side, you can have something like MALDI-TOF, TOF is a mass spectrometer, which is the detector at the end, but MALDI is a separation technique that has nothing to do with LC. So the bottom line is you can have LCs without mass spectrometers, you can have mass spectrometers without LCs, but today we're going to be talking about when they are combined together to create an LCMS instrument system. So what are the main components of LCMS, or liquid chromatography mass spectrometry? I like to break them up into three basic pieces. There is the liquid chromatograph, which is responsible for physically separating compounds or molecules based on something called retention time that we'll talk about. That's in a liquid, so those compounds are dissolved in a liquid, and you have to transition those from being dissolved in a liquid into individual charged ions, either positive or negatively charged ions. And that happens in something called the ion source. And finally, once you have ions, they have to be filtered and detected and quantitated. And that's where your mass spectrometer can help. They can perform what's called mass analysis. And we'll break down each one of these components. And the first one we'll talk about is LC or HPLC. And so when we're talking specifically about LC or HPLC, there are three major components. You have a mobile phase, which is a combination of organics or water with different additives in them. And then you have a stationary phase, which is the physical solid particles that are contained within usually a cylindrical tube that we would call an analytical column. Sometimes it's called an LC column, and sometimes it's just called a column. And those solid particles don't move, so they're stationary, and they have a specific chemistry. There are hundreds, if not thousands, of different chemistries that are available for analytical columns. But functionally, they all do the same thing, where they are are stuck, they don't move. And then you finally have a compound of interest. So some sort of compounds, maybe it's opiates, or so as a drug, or maybe it's testosterone as a hormone. And that compound of interest has a specific affinity to both the stationary phase, so the chemistry that's contained within the stationary phase, and an affinity to the mobile phase. And based on that unique interaction between those two phases, the stationary and the mobile phase, your compounds of interest will travel through that column at different rates. And so this is a breakdown of what that might look like inside an analytical column. So I've basically sliced an analytical column in half, and you can see all those little black dots are representative of the stationary phase. You also have a mobile phase with a flow. So you can see the arrows are pointing from left to right, and they are pushing liquid, so the mobile phase, through this analytical column, and it's getting through all those little solid particles that don't move. And finally, you have compounds of interest. So in this case, I've highlighted 3 different compounds of interest. They're all different shades of blue. There's a light, a medium, and a dark blue. And at the beginning of any chromatographic run, you would see all of the compounds at the exact same spot at the beginning of the column. If you were to think about it in 3 dimensions, it would be like a little disc of material that's on the front of the column. However, as flow goes through, or as mobile phase goes through this column, you can see that some of these compounds start to separate from one another because they have different affinities to the stationary and the mobile phase. So at this point right now, you can see that this column here, let's see if we can highlight it. You can see that this compound right here has less affinity with the stationary phase, so the phase that's stuck in the column, and more affinity with the mobile phase. For example, this compound here is somewhere in the middle, and this compound here has more affinity with the stationary phase and less with the mobile phase. These all then continue to move off of the column, and this is functionally how you would end up separating different compounds with different chemical affinities from each other. One thing I want to call out is the differences between reverse and normal phase chromatography. Normal phase, effectively, the stationary phase that's inside the column is considered polar in the grand scheme of chemistry, and that usually represents non-polar compounds exiting the column first, followed by polar compounds. And that makes sense intuitively. Polar likes polar, and so if your stationary phase is polar, the compounds of interest that are the most polar are going to stay on the column the longest, and so they will exit last. Reverse phase is the opposite. You now have a stationary phase that is considered non-polar, and so everything flips. Your polar compounds have no real interest in interacting with non-polar stationary phases, and they usually exit first, followed by non-polar compounds. The reason why it's called normal phase is that was the phase that was introduced or invented first. And so that's the only reason why we call it that. And so then we just use reverse phase to discuss the opposite. What I can say is reverse phase is usually the most common column that we would use in most analytical applications in clinical. Not to say that stationary phases for polar compounds or polar stationary phases are not used, they're just not used as commonly. Here's another representation of this, and this is where I introduced the term chromatogram. And chromatogram is basically a pictorial representation of what happened in an analytical column over time. And so you have your x-axis here, which is time. You have your y-axis, which we're going to call peak intensity. So basically, how tall does your peak, your chromatographic peak, get? And then here is a pictorial representation of a little column. So you can see at the bottom at time 0, nothing happens. You've introduced compounds of interest onto the column, but that's about it. At time 0, you can't really see anything happening. Let's say at 1 minute, the chromatogram is still recording information and you can't see anything on your chromatogram, but stuff is happening inside your column. In this case, you can see these are 3 compounds of interest. I've denoted them as 3 different colors. You can see a red, a green, and a blue. You can see that the red is starting to separate earlier than the green and the blue. But still, nothing has happened. You can't physically see anything. However, at 2.5 minutes, you can see that your red compound is starting to exit the column and is being recorded on your chromatogram. You can see that your green and your blue are starting to move further into the column. And let's say at 4 minutes, you would see your green compound exiting, and at 6 minutes, your blue compound exits. And so this would then complete out a single chromatographic run where you now have a pictorial representation based on something called retention time. The idea of retention time is how long does your compound of interest retain or stay on your analytical column. And that is one piece of information that we can use to determine what compound that is based on its retention time. So how long does that compound stay on? And as a reminder, because this blue compound stayed on for 6 minutes, it had a higher interaction with that stationary phase than this red compound, which exited much earlier at 2 minutes. So in a perfect world, every compound would separate from every other compound via liquid chromatography in this case. However, that's not the case. Many compounds are exiting the LC column at the same time, and usually that requires a separate layer to be able to guarantee or have high confidence that your compound of interest is the one that you believe it is. And this is where mass spectrometry can help us add that extra layer of separation. Boiled down, what are mass spectrometers actually good at? They're really only good at two things. They're really good at accurately weighing individual ions or compounds. So I like to think of them as a very fancy scale. And they're also very good at accurately counting the number of ions that they measure or weigh. And so they're also a fancy tally keeper. Those are the only two things that mass spectrometers can do. They can tell the difference between one molecule versus another based on its mass, and then they can also count that number of molecules. And so this is where we really talk about mass spectrometry as a technology. And usually the ion source is connected into the mass spectrometer itself. And when we pop open the hood of a mass spectrometer, this is usually what it looks like. Again, you have your ion source, you have your mass analyzer, and your detector. And we'll talk about each one of these specifically. But just as a reminder, you have something called an inlet, which is basically a very tiny tube that is delivering some of that liquid, not all of it, but some of that liquid continuously through the analytical column. So as your compounds of interest and as that liquid flows through the analytical column, some of that gets diverted through your inlet into the mass spectrometer to be assessed or analyzed. It starts with the ion source, which is a reminder of transitioning from that compound dissolved in a liquid to an ion. Your mass analyzer is then able to filter or identify those ions based on their mass. And then at some point, you have to then detect the number of ions that get through or are coming through at a specific time. All of this is connected within a data system, which is a fancy way of saying that it's connected to a computer. So let's start with the ion source. So there's lots of different types of ion sources. I'm just going to talk about one of them, which is called electrospray ionization, or ESI, which is a very common way of transitioning liquid or compounds dissolved into liquid into individual ions. And so as a reminder, starting over here on the left-hand side, so over here, you've got your compounds of interest that are dissolved in a liquid, and they are getting in through that inlet into what's called an ESI needle. A couple of other things I want to call out is that you also have a drying gas. This is usually very warm or hot nitrogen gas, pure nitrogen. And it's inert for a reason. You don't want oxygen involved in this. You don't want to burn your compounds, but you do want them to dry, and we'll talk about that in a second. And you also have some sort of capillary inlet or some sort of a mechanism to get them into the mass analyzer. This is also under a very high vacuum. So the mass analyzer is under a vacuum. And so as you start spraying, you get these little teeny droplets of liquid that contains the compounds of interest that you're interested in. And you have this drying gas that's flowing in the same direction towards the mass analyzer. The mass analyzer is also under a very high vacuum, and all of that combined together causes the liquid droplets to decrease in size to the point where all of the solvent desolvates, so all the methanol or acetonitrile or water desolvates, disappears or evaporates, and all you're left with is charged compounds. In this case, I'm just showing a bunch of compounds that are positively charged. And then those then reach the mass analyzer and then can be assessed for mass and then be counted. So we have ions, that's very exciting. But what do we do with them? So now, once we have ions, we can transition to a mass analysis. And this is where there's several different options for mass analysis and lots of different types of mass analyzers. We've got things like quadrupole mass filtering, we've got time of flight or TOF, we've got ion cyclotron resonance mass spectrometers, and lots of variations and hybrids of the three. So for example, you can have what's called a QTOF, which is a quadrupole time of flight combination. But we're going to focus specifically on quadrupole mass filtering. So this is a scary looking diagram, but I'm going to break it down hopefully fairly easily. So you can see here at this little square is your source or your ion source. This is where, again, just a reminder, your compounds of interest have transitioned from being dissolved in a liquid to individual ions. So you have positive or negatively charged compounds. And then at the very end over here, you have your detector. And your detector is what's going to eventually be able to record the number of ions that hit it. And everything in between is where we're going to call mass filtering. And this is where the magic happens. And so in this theoretical example, I have two compounds of interest. I have one that is red and one that is blue. I'm just denoting them as red and blue. And let's say that your red is 300 mass units. So in mass units, AMUs, atomic mass units, or M over Z, and your blue is 301. So it is 1 mass unit heavier than your red ion. And let's say we ask this mass spectrometer for this time period, we want you to look at masses that are equivalent to a mass of 300. And so that the idea of this is anything that is heavier or lighter, we want to filter. How does that work? So this is where you have a quadrupole. So this is where I can define the idea of a quadrupole. There are 4 poles. You can see 1, 2, 3, 4 poles. And they are in parallel to each other. They are also connected to a set of AC and DC voltages. And when you ask your mass spectrometer to look for a specific mass, let's say mass 300, there is a series of Fourier transforms that are occurring, and the mathematics come behind the scenes in the mass spectrometer to optimize only that specific mass from getting through. And so the way that that works is, let's say that both the blue and the red ions are positively charged. And so as they enter into the mass spectrometer, their first attraction is to one of the 2 negatively charged poles. And so both of them are getting ready to collide with one of these negatively charged poles. But right before that happens, the charges flip. And so the 2 negatively charged poles become positive, the 2 positively charged poles become negative. And now, right before those ions were getting ready to interact with those negatively charged poles, the poles have become positive. They are now repulsed from those poles. However, the 2 poles that were formerly positively charged have flipped to negatively charged, and now those ions are now attracted to those newly negatively charged poles. And this continues to happen. The charges of the poles flip back and forth, optimize for the mass that you want, and you can see that the red ion is basically able to spiral through. It looks like a sine wave, but it's actually more of a spiral that's getting through. But you can see that the blue ion has become unstable. It's called an unstable trajectory, and that ion eventually collides with one of these 4 poles. And in fact, all ions that don't meet that mass criteria of 300 end up colliding with the poles before they reach the detector. And that is the essence of quadrupole mass filtering. You are giving the mass spectrometer an assignment of a specific mass. The mass spectrometer has organized the mathematics to change the charges of these poles in a way that all other ions that are heavier or lighter end up becoming unstable and colliding with these poles, and only the masses that are representative of 300 in a positively charged mode end up actually reaching the detector. The other thing I want to call out is anything that is neutral, so anything that was not charged, has no real attraction to any of these poles and ends up falling out of this pathway before it reaches the detector. So again, you are now only identifying ions that meet that specific criteria that you have asked the mass spectrometer for. So what's the detector then going to do for you? So in this case, detectors are usually electron multiplier tubes. And in essence, when an ion that was able to get through, so was able to be filtered, ends up getting to your detector, it collides with the detector itself, and that releases a shower of electrons. And those electrons, based on some optics, end up colliding with other components within the detector to release more and more electrons, which quickly amplifies the signal. And the easiest way to show that is you've got one ion that enters into your detector, which is an electron multiplier, that releases a shower of electrons. And again, the angles are optimized so those shower of electrons hit another one of these optics, and you can see very rapidly you multiply your signal, usually around 1,000,000 times. And then that signal, which is an electronic signal, is converted into a digital signal and is recorded. And the signal is proportional to the number of ions which are colliding with the detector. It's not a one-to-one, but it is very proportional. The more ions, if you double the number of ions that hit the detector, you double the signal, or at least that is the intent. Okay, so what I showed you was a single quadrupole mass spectrometer application. So that is just MS if you want to define it in that way. What is tandem mass spectrometry, or MSMS, and how does that work? So again, all I showed you was a single quadrupole. Many clinical mass spectrometry methods are using 3 quadrupoles in tandem. So that's what a triple quad means, 3 quadrupoles in tandem. And so going back to this exact picture, what you effectively have done is tripled this specific space where you have now 3 quadrupoles in a row. You still have one source, you still have one detector, but you have 3 quadrupoles. What does that do? Why is that relevant? So this is another pictorial representation of how that can help us. So first of all, I'm showing a new example where you have 3 different ions that are represented in 3 different colors. So each one of these colors is a different mass. And again, everything that's happened here, so this is where your liquid chromatography has happened. You've separated out lots of the other compounds, but 3 compounds, red, blue, and yellow, have shown up at the same time, basically at the same retention time, and they're entering into your mass spectrometer. They've been converted into, let's say, positively charged ions, and now you are trying to filter them. And let's say you just want to look for the blue ion. We've already discussed this. So we've basically said, okay, we want to optimize the mass spectrometer, that quadrupole, to only look for the blue ion. And so any of the other masses outside of the blue ion's mass become unstable and they end up colliding. So yellows and reds are all been filtered out. As a reminder too, I've sliced this in half. There is another pole that is going into the board and another pole that's coming out of the board that you can't see right now. But what if we wanted to take this a step further and we wanted to look at the physicality of that blue ion and be able to ensure that 300 mass, because there's lots of compounds that weigh 300. There's not a lot of specificity just yet. However, if you use the second quadrupole to add an additional amount of voltage, you can fragment or break apart that precursor, which is what we call a compound, the precursor mass, so the largest mass, into smaller product masses. So in this case, I'm going from a large blue compound to what looks like a medium and a small blue compound. And let's say that I just want to then say, okay, each one of those fragments is a new mass, a smaller mass, and let's say I want to just specifically look at that smaller mass. I can ask the third quadrupole to then filter for just the smallest fragment that we were able to detect. And then that is what finally reaches the detector. Why is that relevant? So this is an example, this is hypothetical, but it could happen in real life. So this is where we have three different opiate, either opiates or opiate metabolites. And let's say you have an immunoassay at the very beginning. So I didn't speak about immunoassays, but just to call out that immunoassays use antibodies to detect. And so if you have a drug screen by immunoassay, they will likely detect any and all of these compounds as an opiate, but you really can't tell unless you use mass spectrometry. So we have norcodeine, which is a metabolite of codeine. We have morphine, which could be a drug that can be given to a patient, or it could be a metabolite of codeine. And then you also have codeine itself. And one thing that I want to call out is that the only difference between these compounds is their methylation pattern. So the number of carbons that are connected to either the oxygen or the nitrogen. So that you can see that codeine at the bottom is methylated at both sites, where morphine and norcodeine are methylated just once, but at different sites, where norcodeine is methylated at that oxygen at the top, where morphine is methylated at the nitrogen. And one other thing I want to call out is that codeine's mass, because it's one methyl heavier, weighs 299 mass units, whereas right now, norcodeine and morphine both weigh the exact same mass, or they are the exact same mass. And so let's say we want to try to detect morphine only in the presence of these other two compounds. Well, when we select mass 1, or in the quadrupole 1 for that 285, you're going to very easily get rid of codeine because that's a completely separate mass based on what we talked about. But if you stop here, if you have a detector here, and you're starting to detect this, any norcodeine that is present will also be counted and will also be detected. The detector at this point doesn't care. If it's an ion that meets the criteria based on the filter that you applied, it will be detected. And so if you stopped here, any norcodeine present would falsely elevate the quantitation of morphine that's in this patient sample. But we can take this a step further. If we then use MS2, which is what we call a collision cell, where we add that additional voltage, we can fragment. These are two theoretical fragments, but in this case, you have basically popped off this nitrogen ring here and are left with two fragments that are comparable to each other, but one of them lost its methyl, in this case morphine, whereas the norcodeine compound retained its methyl. And so now you can see that these masses are different. And so again, if we wanted to look for morphine in the MS3, we can ask to look for that 229, and now you are able to detect morphines very specifically. This is the power of triple quadrupole mass spectrometers. You can use multiple mass filters to get to a very specific component. Again, as a reminder, this ion, it doesn't look ionized, but this ion is a precursor mass. And you can see after you fragment it and choose a specific fragment, this would be called a product mass. Selection of precursor and product masses are called selected ion monitoring, or SIMs. These are also called transitions. You may have heard this term before. So going back to that morphine, you can say that 285, which was the precursor mass, and I usually say the word choose. So 285 choose 229 is this precursor and product mass pattern that you are asking the mass spectrometer to look at. So this is one SIM or one transition that you might be looking for. And here's what this looks like in real time. First of all, you now have time on the x-axis and ion intensity on the y-axis. So you can think of this as a chromatogram. This is just now adding the layer of how mass spectrometry works. You can see these little teeth or these little time frames are specific. So each time frame is usually in the millisecond time frame itself. And so if you are asking the mass spectrometer, hey, I want to look at this specific transition for this specific time frame, I now have asked it to go, okay, mass spec, I need you to optimize your optics and your electronics to look for this specific mass, this in quadrupole 1 and this in quadrupole 3, based on that criteria. And the mass spec goes, okay, I'm going to do it for a very small amount of time. And it goes, okay, I'm going to do it, and I'm going to count for this time frame how many ions I was able to find in that time frame. And it goes, okay, ready, set, go, stop. And it counted in this theoretical example 18,943 ions that met criteria for morphine in this case. And now let's say in that next time frame right next to it, it counted 22,462 ions. And now, if you were to look at each one of these time frames independently for that same exact transition, you can see that the ions are being counted, and you can see that they go up to a peak, and then they go back down. And so again, as a reminder, the time is now representative of when a compound of interest is leaving your analytical column, and it usually shows up in a Gaussian-like peak. And you can see that now each one of these individual time frames is kind of a snapshot of how many ions are showing up that meet criteria based on the criteria that you've set for your triple quad mass spec. But I can take this a step further. How do you analyze multiple peaks at the same time or in the same time frame? This is an area that always used to confuse me, that it didn't make sense to me how two compounds could be coming out at the same time and both be detected independently. And so when we think about it, it's really thinking about the scale of time that you're actually looking for. So I have three theoretical masses here. I've got a 567, choose 282, a 483, choose 142, a 215, choose 105. So all of these are combined together. And at the beginning of any acquisition, they're all grayed out, meaning that there's no color, or sorry, there's no identification of any masses at all. But if you are setting this up where you want to look at each one of these compounds individually, you may spend 10 milliseconds of your mass spectrometer to look for this specific transition. There's a 5 millisecond usually pause time where the mass spec, I like to think of it as closing its eyes. It basically turns off its detector and lets all of the ions that were kind of floating around in that space, in the space of the triple quad, to fall out or hit any of the quadrupoles so that you're not counting them. And then the mass spec turns its eyes on again and looks for a different transition for 10 milliseconds. Then closes its eyes, then looks for 10 milliseconds, and then closes its eyes, and then it repeats over and over and over again. And so when you add all of these time frames together, so 10 milliseconds per acquisition, so for each one of the transitions, and 5 milliseconds of pause time where the mass spectrometer closes its eyes, the cycle time is 45 milliseconds when you add all of that together. And that's basically the total amount of time for three transitions to complete one cycle. That basically means for every 45 milliseconds of time, you would be able to get one data point for each one of these three different transitions. And so I'm taking this exact same picture that we showed before, but now I have added colors to functionally denote the differences between each one of these. So now instead of looking for the same transition over and over again for each one of the time frames, you are basically creating a pattern where you're looking at three transitions and then you're starting over. And so functionally, this might look something like this. You're effectively acquiring data, but you can see now you have compounds that are overlapping. They look like they're overlapping, but in reality, they are not. They are being detected in independent time frames that are so small that it looks like overlap when in reality you're actually getting independent acquisitions. And so this might be your chromatogram of looking for each one of these three compounds. One of the compounds was fully separated from the others, but the other two had some overlap, but that's okay because you have independent acquisitions at a very small time scale. Let's quickly talk about time of flight, which is also high resolution mass spectrometry, or that is a term that is used sometimes to describe time of flight mass spectrometers. So getting into just a brief amount of math here, how is time of flight related to mass anyways? So the idea of ions flight time, and I'll show you some pictures of this. It's effectively determined by the acceleration and its mass to charge ratio. So the easiest simplified relationship, and it's much more complicated than this, but the easiest way of simplifying this is that time, which is denoted as t, is proportional, that's what that means, to the square root of the mass over z. And so what that translates to for this education is effectively the lighter, so the lower the mass of an ion, will travel faster than a heavier ion. So heavy ions travel slow, light ions travel fast, and you can capitalize on that time of flight. So if you were able to accurately record how long it takes for an ion to go from one side of a flight tube, which I'll show you in a second, to the detector, can then be back calculated to determine its mass. And this is quite accurate, and this is where it becomes what's called high resolution mass spec. This is my very oversimplified picture of what time of flight looks like. And so just a quick couple of denotions here. So this is your flight tube. It's in the shape of like an upside down V. Sometimes flight tubes are truly linear, but many times they have some sort of reflectron, which basically allows a smaller space to have a longer tube because you basically add bends to the tube, and that gives you a longer tube length, but then crunched down into the size of a mass spectrometer. So this is the whole flight tube. And then at the very end over here, this is your detector. And this is where your ions are entering into the flight tube. So these are ions that are coming from your LC and your source. So again, if you're using LC-TOF, the same applications apply. You have compounds of interest. They've been separated by liquid chromatography. A very small amount of that liquid enters into an ion source, which is transitioning those compounds dissolved in liquid into ions. And now you have ions that are getting ready to enter into your flight tube at this point. You also have something called an ion pulsar, which basically sends what are called little packets of ions in very small time frames to basically be able to say, okay, I'm basically sending out a set of racehorses at a very specific time frame, and then I'm going to count how long it takes for all those little racehorses to get to the detector, and then I can say each one of those ions, racehorses, that ends up hitting the detector. Because I know the flight time and because I know the length of that tube, I can very accurately then back calculate what each one of those compounds weighs. And so this is what that might look like. Here's your little packet of information. So in this theoretical example, you have three compounds of interest. You have your large green compound, your medium blue compound, and your small red compound that, again, are denoted by colors and sizes, which I'm going to also represent based on their mass. So the tiny red one is the lightest, the large green one is the heaviest mass. And you can see at the beginning, let me actually take a step back. At the beginning, your pulsar was, all your compounds were right at the very beginning of this flight tube, but as time goes by, the smaller red ions are getting to the detector first, followed by your medium blue, and then finally your green. And again, all of that timing is recorded, and every ion that then hits the detector is then not only counted, but that is connected to that time that was original at the ion pulsar. And then you can back calculate that high resolution mass because of it. And then it repeats again. So so this is just thinking about time of flight in general. The heaviest ion determines the pulse timing. So what that effectively means is that your time of flight instrument has to wait for the slowest, basically the heaviest ion to reach the detector before you can send another packet of ions. Because if you didn't wait, sending out new packets of ions would then start counting heavy ions that were too slow in that original packet. When those were hitting the detector, they would then be counted as really light ions. So you have to wait. And so this is really where your maximum M over Z range sets the minimum cycle time. What that effectively translates to is if you, because remember, masses of compounds can range anywhere from very light, so 25, 50 M over Z for really, really tiny molecules, all the way into the hundreds of thousands for things like proteins. But if you restrict, for example, small molecule quantitation, restrict your M over Z to, let's say, 1000 to 1500, that's usually the interface where we would consider it not a small molecule anymore, but probably a peptide or a protein after that mass. Then your approximated flight time is 30 to 50 microseconds. So now we're in microseconds. So again, what this is effectively saying is that if you restrict your highest masses that you want to physically look for of ions to this range, your then flight time is about 30 to 50 microseconds. And that then can tell you how many packets of ions you can send in a specific time frame. So in this case, if you restrict that, you're getting 20 to 30,000 pulses per second. That's a ton of data that you end up getting. So you get basically 20 to 30 packets of data that then can all be recorded. And again, expanding to higher M over Z's, so higher masses, so basically expanding your range, it ends up reducing your pulse rate because you have longer flight times that you have to account for. Time of flight mass spectrometers work by then converting these ion pulses into thousands of what are called time-resolved spectra. And then they can transform that flight time into those back-calculated masses and then give you that data sets. These pulses are then summed up and they're averaged into what are called single spectrums. And so usually you're getting 5 to 20 spectra per second. So that allows you to take these really large packets and pulses of data, condense them down into data that is then easier to review. This is what is really important is when you are comparing quadrupoles and time of flights, there are some significant differences. The primary role of triple quad mass spectrometers is what's called targeted quantitation. You have to understand and know what you want to look for. This is great for direct confirmation of, let's say, drugs. So, for example, we want to look for opiates. We know we have a list of opiates that we want to look for, like let's say codeine, morphine, norcodeine, etc. We can have very specific identifications because we have told the mass spectrometer exactly what we want to look for. Time of flight is different. Time of flight doesn't care. It will count and record all ion masses for that length, that time frame, and that can help with what are called unknown identifications, which can be valuable if you are not exactly sure what you want to look for. However, there's always caveats. Sensitivity, for example, triple quads are very highly sensitive for known analytes, where TOFs have pretty good sensitivity, but are usually lower than triple quad for most applications. And that sometimes matters for some drugs where you may not have a high enough concentration of that drug to be detected reliably in time of flight, whereas if you were looking for it specifically with triple quad, you would likely be able to detect it. From a specificity perspective, it's triple quads are highly sensitive, are excellent for MRM transitions. MRM is effectively the multiplication of SIM, which is single ion monitoring. MRM basically means multiple ion monitoring. So effectively what we showed with those three compounds that we looked for over and over and over again. When you have that type of discrete mass data where you're breaking and fragmenting compounds together, you end up with a very strong data acquisition that is very specific. But for time of flight, there's the fact that it's specific comes from the fact that your masses have high resolution. You can accurately determine that exact mass, and that can help with specificity. So from a data acquisition perspective, going back to this, you've got targeted MRMs or SRMs for triple quad, which means you have to, again, you have to specify what you want to look for, whereas time of flight, you have full scan and accurate masses. The best clinical uses for triple quads versus TOFs is that for routine quantitation, when you know exactly what you want to look for, triple quads always are best practice. Whereas time of flights, this is really where you're looking for comprehensive toxicology testing when you're trying to identify unknowns. And from a retrospective review, this is one other component I want to call out, is that it's quite limited with triple quadrupole. You can't really say, hey, if I wasn't looking for flunitrazepam in a benzo assay, if I hadn't defined those masses for flunitrazepam in that data collection, that data was never collected. You would never be able to find it. Whereas flunitrazepam in a time of flight has certain high resolution mass characteristics based on the flunitrazepam's mass, and I can always look back at that data because all of the data was collected. What I can say is that for small molecule quantitation, usually laboratories are really using triple quadrupole mass specs for their routine work, whereas when you are really trying to identify broad spectrum testing, whether it's research or whether you're in a very large toxicology laboratory that is servicing a complex group of patients, time of flight may make more sense. Mass analyzers can be quantitated. This is the last kind of piece of this. So when you use a calibration with standards of a known concentration and you add something called an internal standard, this allows for quantitations of the sample to be analyzed. How does that work? So what's an internal standard? So first of all, I'm showing morphine and its internal standard morphine D3. The only difference between these two compounds is that the morphine D3 has three what are called deuteriums that have been replaced that have replaced the hydrogens, and they're actually replaced here. So there's D3 and these are the CH3. Deuterium is an isotope of hydrogen. Hydrogens usually have one proton and one electron. Deuteriums have one proton, one neutron, and one electron, and that effectively makes deuterium's mass one mass unit higher for every deuterium that is replaced. And so if you have three deuteriums that have replaced three hydrogens, your morphine goes from 285 as a mass to 288. What's magical about internal standards, or at least the intent, is that they are nearly identical in terms of their chemical properties. What that usually means is that they are retaining the same amount on an analytical column. They usually ionize nearly identically. And the only difference is that their masses are different. And that allows us to quantitate them separately. But why would we do all of this work? So let's talk about when we think about these two different masses, we have to ask the question, how do ion counts become concentration values? How do we translate these ion counts into something that's quantitative? So we end up using that peak area. So now you have those analytical peaks that were detected by mass spectrometry, and you can integrate them, that area under the curve, and that's calculus. Again, that's happening behind the scenes within your mass spectrometer. That's not something that you are required to do by hand, at least not any longer. You can get ion areas under the curve for both your analyte of interest, let's say morphine, and the internal standard that you added, so morphine D3. So you're getting two different area counts, and you can create a ratio based on that, those two area counts, and that can be plotted versus concentration. And this is where, if, for example, you were adding all of these internal standards to calibrators, you would then be able to do that same process for unknowns like QC or patients and analyze them in the same way. And you can then back calculate that ratio to the concentration of an unknown sample. But what does that look like? So here's an example of amphetamine here. So for 100 nanograms per mil of amphetamine, actually, let's just add all of this in here. Okay, so for 100 nanograms per milliliter of amphetamine, You can see that there are three different calibrators in this particular case. So you've got a 100, a 500, and a 1000. And so if you were to add the same volume of internal standard before you begin acquiring this material, these samples, so this would be part of your sample extraction. And you have this 100 nanogram per mil of amphetamine, and you have added a given amount of internal standard. Let's say you then analyze that specific sample, and let's say you're doing this by triple quad mass spec. You were able to get 25,000-ish counts of amphetamine and about 1.2 million counts of amphetamine D5. So remember, this is a deuterated internal standard, and it's 5 deuteriums. You get a ratio of 0.2. You can see for your 500 nanogram per mil amphetamine, your number of ion counts for amphetamine jumps, and that makes sense. You have quintupled the amount of amphetamine, and you've roughly quintupled the amount of counts. You can see, though, your amphetamine D5 hasn't really changed. It's still about 1.2 million counts, but that makes sense because you added the same amount of that internal standard to this separate calibrator. And finally, for your 1000, you've effectively doubled your ion counts to 260 from 125. And you can see that your ion counts have roughly stayed the same for your internal standard. All right. So let's talk about what that looks like in a standard calibration curve. This is a very tiny picture, and I apologize, but let me call out that on the x-axis here is that 1000 nanogram per mil calibrator, and you can see that you got an area ratio of 0.2. So you can see that if you divided that area ion count of your analyte divided by your internal standard, you would get an area ratio of 0.2. And you can then see that we have, in this case, we actually have 4 calibrators. We have that 100, the 500, the 1000. We also have a 5000, and they are all creating linearly increasing ion ratios that are dependent. And so let's say we then have an unknown specimen, and the idea of an unknown is we have no idea what that compound of interest is in terms of its concentration. But if you prepare it in the exact same way and you add internal standards, you can see that the area ratio is 0.5. And then you can back calculate that to say that this patient's sample had 2,700 nanograms per milliliter of amphetamine based on the calibration curve, which was based on the acquisition and designed in this way based on our pre-analytics where we extract with a specific amount of internal standard. So a couple of final thoughts. That was a whirlwind of how clinical mass spectrometry works in the briefest of ways. But LCMS and mass spec are providing complementary layers of analytical specificity. They are both really important in most small molecule quantitation applications to be able to have enough specificity to tell us whether or not our compound is the compound that we think it is. Chromatographic separation is reducing interference, while mass spectrometry is really providing that molecular level identification based on mass. Triple quads excel at high sensitivity targeted quantitation using MRM transitions, and that's still kind of the bread and butter of many of our quantitations in clinical laboratories. And then time of flight are enabling screening for an unknown identification and then allowing you for retrospective analysis, which is a valuable tool in some clinical contexts. And with that, I want to thank everybody for taking their time to talk with me about clinical mass spectrometry, and I am happy to answer any questions.